Hey guys, so I want to go over the Chapter 10 topic towards the end where we were going over gas equilibrium. I feel like I didn't explain it in as much detail as I can. So up until this point in Chapter 10, we learned about aqueous solution equilibrium and how if you add reactants, increase the temperature, decrease the temperature, what happens to the equilibrium? Does it shift to the left or to the right? And remember, that is based on the equilibrium constant. So remember equilibrium constants where K equals the ratio of the concentration of products over reactants. Now, if you have our equilibrium of A plus B, double arrow, let's say equals C, the concentration of the products divided by the concentration of the reactants at equilibrium determines the equilibrium constant. If C is much higher in concentration, let's say all the reactants react and you have 100 molecules here and only maybe 1 or 2 here, you're going to have a large equilibrium constant. But if you have it the other way, and let's say with a weak acid or weak base, so weak acid slash base is going to have a small K. And that's because you have a very small dissociation. So if you have a weak acid such as hydrofluoric acid, you're going to have a very small dissociation of HF into H plus and F minus. And this is what you'll have, like, let's say one molecule here, one atom, and then you'll have 99 of them still that are not dissociated. So your concentration products over reactants will be a very small number over a very big number, making a very small equilibrium constant. But for gases, we want to look at this in terms of our ideal gas law, our Boyle's law, Charles's law, Gay-Lussac's law, combined gas law. We want to think about it in terms of pressure and what's happening to the movement of the gas molecules. So let's go through this quickly. If you want to add or remove a gas, let's just say gas A, right? Ag plus Bg yields gas Cg, right? And let's just say there's 3 moles of this, just to make it interesting. And this is a pretty comprehensive example. All right, so if we want to add, and let's say the equilibrium constant for this one is just some number. So equilibrium K equals 2, right? That means the ratio of the products over reactants when the equation's at equilibrium is going to be 2, more towards the product side. So let's say we add this. Let's say we add gas A, right? If we, case 1, we're going to add A. If we add gas A, what's going to happen to the container? Remember that this is a container that has gas A, B, and C. So it's got a bunch of different gases, and they're all at equilibrium at an equilibrium pressure. So we want to think about it in terms of pressure. If we add a reactant, we're adding more. In order to relieve the pressure that's created, what we're going to do is we're going to, since we have a lot of A and let's say we have a lot of B, whatever the excess of A is going to force to react with B, with whatever's left of B, to create C. So there's going to be basically the same thing for Le Chatelier's principle here, where if you add a reactant, it just goes the opposite way. If you add a product, it goes backwards. So just to keep the equilibrium. So that's pretty straightforward. Let's look at volume. So let's take the same equation. Let's see if I can copy it. I can't, whatever. So let's do the same equation. This is where the rules begin to differ a little bit. So let's say Ag plus gas B, G is 3Cg. All right. So this is where the number of molecules on each side of the equation at equilibrium come into play. So let's say if we increase the volume, right? Increase volume. The rule is that the equilibrium shifts towards the direction of the most moles. So what that means is if you look at the reactants, the number of moles here based on the coefficients, you have 1 plus 1 is 2. In the products, you have 3. So that's pretty easy to see that the products have more moles. So if you increase the volume, the equilibrium will shift towards the right in this case only because the products have more gas moles. So the reason why that happens is, let's take a look at a flask, a beaker, right? You have all of these in a beaker. Let's say you put a piston in here and you press down on this piston to decrease the volume. Oh, sorry, press up, my bad. If you push up on this piston to increase the volume, what's going to happen is the piston. These gases are going to have more room to breathe, and the pressure is going to decrease. So from state A to state B, the pressure decreases. In order to make the pressure higher again, to make this reaction at equilibrium, it wants to go, the reaction wants to go towards the direction that makes the most atoms and makes the most molecules. Because what's going to happen is, remember, if we assume all these are ideal gases, you have a very, very small particles, and it doesn't matter what type of gas they are, it just matters the number of them that creates the pressure. Because relative size to each other is very small. Difference in relative size, it doesn't make a difference, really. So the idea is that the increase in volume decreases the pressure of the entire mixture. Once that pressure is decreased, that means in order to increase it again, the reaction has to shift in the direction that makes the most molecules to cover up that space. So the reaction actually thinks, all right, since we have reactants here, we have 2 moles here, if we react these together, we can make 3 moles of this. That's more valuable right now because we need more moles in order to offset that pressure decrease caused by the volume increase. So I hope that makes sense. Now, if volume is decreased, the opposite happens. So it shifts. This is the equilibrium, and the equilibrium shifts towards least moles. And what that means is, if you have the same case, this is going to be the increasing, this is going to be decreasing, and you're pushing down on that piston, it's going to be down here, you're pushing down on the piston, what's going to happen is the pressure is going to increase, right? Everything is going to be forced closer together. Once that pressure increases, in order to offset the increase, the reaction is going to be like, wait, we need less molecules. We need less moles right now. Because we want to lower our pressure, we need to make more space for everybody by making less moles. So it'll go towards the direction of least moles. So I hope that makes sense. Now for temperature, it's very similar. Let's look at this example. Well, let's look at, whatever, I'll just make new things. So for temperature, if you increase the temperature, what's going to happen? It increases the pressure. So it's going to be the same thing. So increase in temperature equals increase in pressure because you're going to have more collisions with the container, right? The faster the molecules are, the more collisions with the container. The more collisions with each other, you're going to have an increased pressure. That increased pressure means that that means the reaction wants to decrease the pressure to offset the increase in pressure caused by the temperature increase. Therefore, the reaction will go towards the least moles. I'll put least moles. And if we decrease the pressure, the temperature, that means the pressure is also decreased, right? Remember P over T? That's an R. That looks like an R. P over T. P over T, right? So we didn't really go over this law. I think we went over V over T, but P1, yeah. It's still a law, too. This is called, it's a different law, but they're directly proportional, is what I'm trying to say. So temperature decreases, and then that means the pressure is going to decrease, the molecules are moving slower, they're making less collisions with the outside of the container, or the inside of the container. That means, in order to offset that pressure decrease, the reaction is going to move its equilibrium position to the direction of the most moles of gas in order to fill up that space, in order to maintain that equilibrium pressure that was lost from the decrease in pressure, in temperature. So I hope that makes sense. This is just a short video. I will post the grades for the tests soon, within the next day or so. All right, so good luck with everything, and I'll be posting another lecture soon for just like a medley of information. Not really for the exam. All the final exam stuff has been covered already. All right, bye.